All right. Well, hey, welcome to another fun-filled week of modern physics. Happy Star Wars Day. May the 4th be with all of you as well. So today's plan, we're going to keep talking relativity, right? Last time we got to the whole idea of how time gets affected. So we saw that simultaneous events aren't necessarily simultaneous anymore, depending on your perspective. And we saw that clocks are going to run at different times, which is definitely trippy. So we're going to continue there. I'm going to share with you what's called the twin paradox. And then after that, we'll look at how these two simple ideas, right? The laws of physics are still applicable to every reference frame, and that the speed of light is the speed of light no matter where we are. That those two simple ideas are also going to affect how lengths are perceived, which then if times and lengths have issues, then so too will velocities. And if velocities, then, momentum and energy and right. And so we're going to just sort of continue down that path. But before I do that, any questions about any of the homework? Hopefully you did see I did change the homework dates to what I intended them to be. So chapter 4 is due Thursday this week, and then chapter 5 is due Tuesday next week. So I apologize for that, but thank you for letting me know about that, Ralph. But anyway, any questions about the homework or anything else we talked about so far?
Yeah, could we go over problem 38 on chapter 4?
Absolutely. All right, so let me go ahead and switch my screen here so y'all can see it. All right, so I'm sorry, which one did you say, 38? 37.
Yeah, 38.
38, okay, thank you. So 38, a monochromatic light of wavelength 589 nanometers is incident on a double slit with 2.5 micrometers and unknown separation. Okay, so we've got our two slits, but we don't know how far apart they are. So that's what we're trying to find out. But then it says it results in a diffraction pattern containing 9 interference peaks inside the central maximum. And then we want to find the separation of the slits. So just to kind of remind you like what all those different terms mean, because it has been a little bit since we've seen them. So double slit experiment, right? So we got our two slits. And as light passes through those two slits, they are going to interfere with each other and give us bright, dark, bright, dark, bright, dark, bright, dark. But we also saw that if we just send light through a single slit, that also leads to a bright, dark pattern, right? That's the diffraction part. But when we combine these, what we're going to see is sort of a central brighter area that's made up of bright dots. Those bright dots are going to dim down, and then we'll see more brighter ones and then dimmer ones. Okay. So what this is specifically saying is in that first middle bit, we see a bunch of bright darks, but then they all die out. And the question is, how many of them are, since we have, was it 9 of them? The question is, okay, can we figure out how far apart they are? So I'm just curious, because you guys said you were going to redo this lab on Friday. Were you able to kind of see that better?
Yeah, I think so anyway.
Because now you knew what to look for, and you could see those bright go into dark, right? And so I showed you those pictures before, so hopefully you kind of remember that. But anyway, so that's what our goal is here. So let me go ahead just real quick and write down some numbers here. And then I'm going to go to a whiteboard and see what we can do with this. So real quick, we got a wavelength of 589 nanometers. The slit width, 2.5 micrometers. We've got 9 peaks in the central max. And the question is, what is the separation of the slits? Okay. So let me go to a whiteboard and let's see what we can do here. All right. So real quick, the picture. Right, we got those, and then over here. And so then in terms of the bright spots, we're gonna have the one bright, big, bright center one, 2, 3, 4, 5, 6, 7, 8, 9. All right. And what we know is that then at this point, like if you were to graph the intensity of the light because of the interference, you would see something like this. So are you guys all cool that I'm kind of doing this sideways? Right, so this is our intensity. And so again, we've got between here and here are those 9. All right, so how do you think we can answer this question? Ideas, thoughts, suggestions?
Maybe find an angle first.
So when you say find an angle, what do you mean by find an angle?
Like maybe find an angle between the bright fringes.
Okay. So when you say the bright fringes, do you mean the dots or the like where it dies out?
I guess maybe where it dies out.
Okay. So on the picture then, what you're saying is like that angle?
Yeah, something like that. Because then maybe we can use some trig to find the spaces in between.
Okay. And like, okay, let's just sort of break this down and let's think about the two different things going on. When we've got the diffraction, just because we're passing through a slit of any kind. And then we get the interference that's coming from the double slit. And we've got a couple of different formulas for those, right? So if you think about the double slit deal, we can use double slit to figure out the distance between these things, right? The double slit formula definitely lets us calculate those. And then the interference bit lets us calculate distance between dark spots. So I think that's what I would recommend. I would go with the, all right, let's figure out how those things relate. And if we're going to have 9 of these compared to this one big distance, maybe that can help us figure out the separation. All right, so let's go back to the book and let's find some formulas here that are going to help us. So these are definitely not things that I have memorized. So I'm going to just go back to the book and find these guys. So let me go ahead and share that with you guys again. All right, actually, let me go back up to section 4.1. So single slit diffraction, right? When we did this derivation, we definitely have our angles to the destructive. So to our dark ones are going to be based on this. And we know that D is the slit width. And we were told that. We were told that that was 2.5 micrometers. So we don't know theta. We also know the wavelength, 89 nanometers. So we can find those dark spots, those first dark spots, by letting m equal 1. So Bradley, when you said find the angle, I don't know if this was kind of what you were going with, but we can definitely use this formula to figure out what those angles look like.
Yeah, that's pretty much what I was referring to.
Okay. So we can definitely calculate that. And then if we go back, let's go grab the formula from interference, double slit. Where is it? I just don't want to have to rebuild them. Here. Let's find the one with theta. Here it is right here. Okay, so if we want to find those similar angles, and for this one, since we're going with d sine theta equals ml, those are the bright fringes. This d is the separation between the slits, which is what we're looking for. But we can use that same sine of theta to help us figure out which one we're looking at. All right, so let's go back to the whiteboard. All right, so we've got 2 bits to this. So I'm going to just go ahead and do them separately. So if we go with the interference pattern, right, we've got d sine theta is equal to m lambda, and we're going to let m equal 1 to correspond to the first dark spot. So that makes sine of theta equal lambda over d, where d is, or big D, is the width of the slit. All right, so that wasn't interference. That was diffraction. All right, now if we go to the formula for interference, it's exactly the same, except it's a little d. And little d is this distance right there. So this is going to be the same sine of theta. We're going to basically go to what should be showing up here. So the question is, what number do we put in for m? Is it 9?
I don't think so. Should be 5, I guess.
All right, so Victor thinks 5. You can tell there's question though in that voice, right? Why 5?
There's 5 dots from the place where measure the angle.
Okay, so let's think about from that center, because we definitely want to split it in 2, right? And so if we count though on either side of that, we actually have 1, 2, 3, 4. But you are right that we want to use m equal 5. Because the next one is going to be the one that we don't see, because that next one lines up right at this spot. So we are going to use little m equals 5. So that would make sine of theta equal 5 lambda over little d. And now we can actually equate those. So we're going to get lambda over big D is equal to 5 lambda over little d. And I think we were trying to find little d, right? So if we just cross multiply, divide by the lambdas, we get that little d is going to equal 5d. So basically, we're just connecting these two things. We're taking the interference pattern that we're seeing for the double slit, and we're comparing that against the diffraction pattern we would see for the slits of that width. And there's the relationship that we get. And in fact, if you had, and I doubt you guys did this, but when you had that double slit set up in lab, I'm sure you calculated the distance between the dots to help you figure out the separation distance of the slits. But you probably didn't try to calculate the width of the slits. But you could have if you had looked for the, okay, where does that brightness intensity drop off to 0? And then you could have used this relationship to find that. So what you might want to do, and I don't know if this is going to be possible. Well, it's definitely possible. If you're curious about this, because you probably still have your numbers and everything, and you might even know from the little disc that you turn to get your slits and everything. You should definitely know the distance between the slits, but it might even also tell you the width of the slits on those dials. I think it does. And you could take those two numbers and figure out what kind of pattern you should see if you remember how many bright spots there were before it died off. Because that's definitely important. That affects the M, right? This guy down here. So again, I don't know if you paid that much attention to your actual pattern, but that's what's driving what you see, is both the separation of the slits and the width of the individual slits themselves. Anyway, is that better for that one, Bradley?
Yeah, much better. Thank you.
Does it at least make sense?
Yes, definitely.
All right, I will take that. All right, any other homework questions? No? All right. Well, that's cool. Well, then let's keep talking about relativity, and let's continue this discussion of, the time is changed and isn't the same for everybody, and what that actually means in terms of the consequences. So before I hop up to the whiteboard, I want to just present this to you. All right, so suppose that there are two twins. All right, so I've got my evil twin who's not just in the mirror, but actually here. So it's going to be me and my twin brother. I don't have a twin brother, but me and my twin brother. Okay, so here's the deal. My twin brother is going to stay on Earth, and I'm going to go explore the universe because I'm that kind of guy. All right, so I'm going to go take off in my spaceship, and I'm going to be gone for a few years, take a few years journey to go get to some star, and then I'm going to turn around and come back. Okay, now we already saw with the time dilation deal is that when something is moving relative to you in an inertial reference frame, time doesn't behave the same, right? And whoever's keeping proper time, do you guys remember what proper time was? Who keeps proper time?
The person where the event starts and ends in the same place.
Okay, good. So if the time is going to be, let's say, the time between heartbeats for me, then I'm going to have proper time because my heartbeat, dunk, dunk, it's happening at the same location in space, so I've got proper time. So if I'm cruising through space super fast and I've got my proper time, my evil twin on Earth is going to say that heartbeat took longer, right? Time dilation. We multiplied by that gamma, and hopefully you remember gamma. As your speed increases, gamma gets bigger. It's 1 over the square root of 1 minus v over c quantity squared. But anyway, so what's going to happen if I'm keeping time, and let's say, you know, I've got a metronome, a clock, whatever on my spaceship, that's at the same place. I'm keeping proper time. My clock is going to say, you know, let's say 5 minutes went by, where my evil twin is going to go, no, it was more than 5 minutes. It's going to be 5 minutes times whatever your gamma is. All right, so let's say that I'm going at 0.99 C. So I'm hustling. So that makes gamma 7, right? So I go out, I'm exploring the universe, I come back, and I was gone, according to my clock, 5 years. All right, so I'm 5 years older now. How much older is my twin?
35 years older.
35 years older, right? So all of a sudden, my twin is an old, decrepit man, can barely walk, and I'm still spry and doing my thing, right? Okay, so that's how this plays out. Now, I want you to think about it, though, from the perspective of, or let's switch that perspective. All right, so my twin on Earth is watching his clock. And he goes, okay, 5 years have gone by. But me on the spaceship, what should I say? How much time should have happened on my clock if 5 years happened on his?
A fraction of that, right?
Not a fraction of it. It should still be 7 times, right? Because according to me in the spaceship, it's my twin that's flying by at 0.99 C. Right? I'm stationary. So I'm watching my twin. My twin's looking at his watch and goes, oh, 5 years have happened. And I'm going to go, nuh-uh, 35 years have happened. Right? Because relative to me, he's moving 0.99 C. And this is what we call the twin paradox. Because both twins are going to go, the other one aged 7 times as much as me. But that can't happen. Right? So the question is then, what's wrong with the relativity? Nothing. Right? Nothing's wrong with relativity. So then the question is, well, how come these aren't jiving? How come we're not, you know, we're getting such different results? Do you see what the issue is with this example?
It's the proper time thing, like who's stationary versus who's not, right?
Kind of, but not really. Because the proper time, both of us could be keeping proper time. Right? It just depends what we're measuring. If my twin on Earth is measuring time, you know, measuring his heartbeat, he's got proper time for that event. If what we're measuring is my heartbeat, then I've got proper time for that event. Right? But again, regardless, if we just go with our heartbeats are exactly the same length and time if we're stationary. Right? That's why we do the thought experiment with twins. We just go, oh, they're identical in every way. Then I'm going to say his heartbeat took 7 times as long as what he says. And in reverse, he's going to say my heartbeat took 7 times as long as what I said. So if I'm measuring time according to my heartbeat, so I'm measuring my own time, he's going to claim that his time went 7 times as long. But then I, in return, go, so let's say, oh, I say 1 second has passed. And he goes, nope, on my clock, 7 seconds has passed. Well, that's his proper time. So then I'm going to go, oh, no, 7 seconds hasn't passed. 49 seconds has passed. But do you see the problem there? Because I started by saying 1 second has occurred. And now using this relativity thing, I'm saying, well, no, actually, no, 49 seconds have happened. But if I said 49 seconds happened, he's going to go, nuh-uh, 343 seconds have happened. Because we just keep multiplying each other's time by 7. That's a problem, right? Because if I said 1 second goes by, no matter what he says, at the end of the day, if I translate it back to me, it still has to be 1 second has passed. So there's a problem. Hence the paradox, right? It can't be we're both saying each other is moving 7 times as fast, or time is passing at 7 times as quickly. So how do we fix that? And just so you know, these are the things that when Einstein proposed this, these are the things that all the little cabal of physicists are sitting around going, all right, let's talk this through. These are the things that came up. And like you think about this paradox, immediately you're like, oh, then something's not right. This theory definitely doesn't hold. But it still does, because there's a fix to it. Anybody can see what it is. And I'll give you a hint.
I think I got it.
Okay, before I give you a hint, then what do you got, Bradley?
Distance.
Nope, not a distance problem, but I like how you're thinking. It's much more basic than that. It has nothing to do with actual any kind of a measurement. So here's my hint. Think about me in the spacecraft and think about my reference frame.
Well, you're the one actually moving at the 0.99 C. Whereas
I
the
mean,
twin
I'm
on
moving.
Earth isn't relative to you anyway.
Oh, but they are relative to me. Right? Like here's how the twin sees the world. The twin sees he's not moving. And I'm moving at 0.99 C. I see the world as I'm not moving, but he's moving at 0.99 C. And that's the thing about relativity is that who's moving? Yeah, both are really. So this is kind of a toughie, right? Like, I don't know what's going on. Well, go back to the postulates for Einstein, right? The two things that we're going to say. So again, all the laws of physics are the same and C is C. What kind of reference frame did we need?
The one that is in movement, how you call it?
Okay, so it can definitely be moving, but it can't be accelerating. We call it inertial reference frame, right? Where things don't just magically start moving. And when we were talking about like the car example, you know, you turn the corner and now the stuff on your dash just, you know, moves across. It appears to move, but that's because your reference frame is accelerating. So think about my spaceship. I go out into the universe and then I come back. I'm not in an inertial reference frame. My spacecraft is not in inertial reference frame.
It's going to have to accelerate and decelerate at times.
There has to be some sort of change in my velocity for me to come back, right? Because think about Earth, leaving Earth, let's just say I'm going this way. My velocity is pointing in this direction, 0.99 c. When I come back, my velocity has to be pointing the other direction. That's a change of velocity. Acceleration happened. I'm no longer in an inertial reference frame. So that means all of my watching my twin on Earth and coming up with these grand numbers, no, I can't do that. But my twin on Earth, who's watching everything go by and seeing me fly off and then come back, his observations are going to be correct because he's in an inertial reference frame. Okay, so it turns out that there actually isn't a paradox because the act of me accelerating in my spacecraft to come home changes everything. It completely changes everything. So we got to be really careful when we're talking about relativity. We have to pay a lot of attention to the reference frames because as soon as you're in a reference frame that's accelerating, right, and I don't care how the acceleration is, but if it's accelerating at all, whether it's changing speed, changing direction, whatever, that's going to affect observation. Now, before you go to the, yeah, but here on Earth, we actually are accelerating because we're going around the sun and blah, 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 blah.
That's what I was just thinking.
Take this as a, like, zoom out. Does it look like we're accelerating? Like if I'm on a spacecraft and I go 5 light years away and I'm looking back at the Earth, does it look like the Earth's accelerating?
Not at all.
No. I mean, it's a pinpoint. And so there is sort of a degree of acceleration that's allowed, right? Like, which again, it's all relative. Hence the name relativity, right? It's all relative to, I mean, everything, right? But it does turn out that in that situation, the twin on Earth is actually keeping or is observing things properly. So I go off, I fly away for 5 years and come back, and my twin is going to be 35 years older. So I'll be looking at an old man. Okay, older man. But I'll be looking at an older man, even though I was like, dude, only 5 years went by. And he was like, well, that's not true. 5 years on my clock, on my calendar, actually equated to 35 years on his. So I don't know about you guys, but I can just imagine. Can you imagine being, one of these people that goes and explores space and comes back? How do you wrap your mind around that? That you leave, you come back, and everything's going to be different, right? Think about what the world was like 35 years ago.
I have no idea. I wasn't born yet.
Way back, I know for all you youngsters, way back in the middle of the 1980s, you guys weren't even alive yet. But let me just tell you about a little bit of the technological world. Cell phones, no. I think some people started to have like car phones, but they were like crazy expensive and only super rich people had them. But oh no cell phones. The internet, no, didn't exist. Laptops, nope. Some people had desktops, but they like the power in a desktop back then would have been like the power in your TI-89, give or take. Right? A lot of phones were still rotary phones, and I know none of you even know what I'm talking about. but the phones back then, you actually had to like spin the dial to make the, to get the numbers. Right. So in terms of technology, oh my God, everything was completely different. So imagine now leaping forward 35 years. I can't even begin to picture what 2056 is going to look like. Right. Well, I don't know. At the rate we're going backwards, I feel, but we're going to be back in the Stone Ages by then. But yeah, I can't even imagine what that'd be like. Or everyone that you knew, all of your friends, like lots of them are dead. Just because time passed, and the ones that aren't dead are going to be like old, and like you just have nothing in common with them anymore. I mean, that would be crazy. Your kids would be older than you. Like think about that, Bradley. Your son, he'd be older than you. You go away for 5 years according to your clock, and 35 happened for him. He's older than you.
That'd be gnarly.
That would be crazy.
Yeah, that'd be gnarly.
Generation skip. Or it's like, oh, my grandkids are my age. What? How does that even happen? I didn't even have grandkids when I left, and yet, so I'm not saying you're going to have kids, Ralph. I'm just saying that because I know Bradley has one, but and never say never. I didn't think I was going to have children, and then next thing you know, I got 2. So anyway, so it's a trippy thing. I know it's a trippy thing, but it's definitely true, right? And we got the formulas for it. All right. Well, anyway, let's move on to other things, because we could sit here and talk about time and the effects of it forever.
I have a quick question.
Yeah,
I'm
sure,
a little
go for it.
confused. So in the whole twin case, one's on Earth, one's in the spaceship. Which one is going to be aging?
So the one aging faster is going to be the twin on Earth.
Okay. Even though it had been 5 years, right?
So it's 5 years according to the spaceship clock.
Okay.
But 5 years on the spaceship clock is going to be 35 years on the Earth clock.
Yeah, that's gnarly.
Yeah.
Okay. So
I
Close
don't
Encounters of the Third Kind nailed it.
Did it? I haven't seen that movie in forever. I'm trying to think what you were talking about in terms of the.
Well, at the very end of the movie, the spaceship lands, and then all the abducted people come out, and they're the same age.
Oh, yeah. That would be fairly accurate. Yep.
Crazy.
So you would, you get abducted by aliens when you're 10, and they go cruise the universe for a year or 2. And to you, like barely any time has happened. But on Earth, there's like, oh, wow, man, you've been missing for 15 years. No, I haven't been gone for 15 years. It's like, maybe you want, so yeah. I guess that is definitely accurate. I don't remember that part of the movie, but it's been forever. I just remember making the Devil's Tower out of mashed potatoes. And when I saw that in the movie, I started doing it every time at home when we had mashed potatoes. And yeah, my mom was not a huge fan of that. Anyway. All right. So let's talk about length and what happens with length. I was going to get up and go to the whiteboard, but we'll do it here. All right. Let me go ahead and clear this real quick. And let's talk about what's going on with length. So we're going to do the same thing that we've done many times, where we're going to have our train car that's moving, and we'll go ahead and say that's moving at some velocity v, whatever. But what we're going to do now is we're going to measure something that's inside the train car. And the way we're going to measure it is we're going to send a light pulse. Okay, so we're going to have like a little laser here that's going to send out a pulse, reaches a mirror at the other end, and then bounces back. And if our time calculations are precise enough, this will give us a very good idea of how long it actually is. All right, so that's the idea. That's how we're going to do this. And just like before, we're going to have the physicist who's riding in the train car, who's actually doing this, doing this experiment. And then we'll have another physicist who's outside watching the experiment happen. And we're going to look at what their two different experiences are, because they're going to be different. So let's start with the one who's in the train car. All right, so the physicist that's in the car, let's look and see how they're going to perceive the length of this. So let's just think about first the distance that the light travels. It's going to go from one end to the other and then back. So that's going to be twice its length. Okay, so I'm going to write here 2 times, and we'll call that L naught, just like we did before where we had a T naught and a T1. We'll do the same thing here. So L naught, that's the length of this thing as measured by the physicist in the train car, right? She goes and she takes a ruler. Hey, this is 1.5 meters long, right? So L naught is her length. Now we, if we had our little ruler, might hold it up and go, oh, we might get a different length, but we'll call that L1. All right. So in the car, we had 2 times that length. Well, that's going to be, C times the amount of time that the physicist in the car measures. Right? If we've got our stopwatch, light goes at speed of c times that time is the total distance traveled, which is going to be 2L naught. So it's really easy calculation, right? It's just 2 times that length is going to equal c times the time as measured in that car. All right, so now let's change our perspective to the person outside the car. Outside care. Outside car. So let's think about what we're going to see. So at the very start, the light is going to leave to start going to the mirror that's at the other end. But if you think about what's going to happen, let me just draw it back down here a little bit. So we started with, here was the length that we are going to try to measure. But the mirror is moving because the car is moving. And so if we look at that light that leaves here and goes, it's not actually going to hit this point when it returns. It's going to go a little bit further because the mirror and everything on this length is going to go a little bit beyond. Does that make sense? Right?
Yeah, similar as the last case, right? It's going to appear longer.
So here was that. It's going to go a little bit further because this went this way. So by the time it hits the end, the mirror that's on the end, let's move forward a bit. Okay, so if we look at that distance, we'll go ahead and call that distance D. Think about what it's going to be made of. It's going to have the length, the original length, but, and I should actually call that L naught. No, that'll be the length we see. So it's that length. So we'll call it, say, L1 plus whatever extra distance is traveled. Okay, well, that's going to be the velocity of this train car times however much time we say has happened. So are you guys good with that? So it was the original length, but then we have to add on a little bit more because it's moving.
Don't we need to account for the light returning as well?
We do. And we'll take care of that in just a second. All right, but this is going to be the same as the speed of light times however much time passed on our clock, right? Because we're seeing that light pulse move from one end to the other. We're timing it. So that distance is c times our t1. So we can actually solve that for t1 for this time. It's going to equal L over c minus v. If you just like bring this over L1 divided by c minus v. So that's how much time it actually takes for the light to start and then hit that mirror as it's moving forward. All right, so, but now what about Bradley? Just saying, well, what about the return trip? Okay, well, the return trip, so let's just do this, so return trip. For the return trip, the distance is actually going to be L1 minus V times, and I'm going to call this T2, because this is going to be the time going back. And the reason that it's minus is now that back end is moving forward. So it's really shortening the distance that the light has to return back. And again, that's going to equal C times T2. So we can solve that for T2. And it just ends up being L1 over C plus V. And this should totally make sense. You look at these formulas, C plus V is bigger than C minus V. So dividing by a bigger thing gives me a smaller number. So I should expect less time for it to come back than to go out. All right, so then the total time that we're going to calculate is going to be the T1 plus T2. So that's going to be L1 over C minus V plus L1 over C plus V. And I can, get a common denominator, put it all together. And what it ends up being, and you can just kind of trust me on this one or do it yourself. I don't really care. All right, so this is the actual total time that we're going to see happen outside the car. So the pulse leaves one end, goes to the other end, and bounces back. What we read on our stopwatch is going to be this formula right here. All right, so we really have both of these times, right? In the car, it's 2L naught over C, and outside of the car, it's this horrible formula. But we know how these times are related. Those times are related by the time dilation formula that we had before. So let me just put that up here. What we saw when we actually looked at time dilation was the time outside was equal to gamma times the time on the inside. And in terms of proper time, right? Who's calculating proper time here?
The physicist inside the car.
Right. The one who's in the car has proper time because the event, the light beam, starts and ends at the same place relative to her. They both started at the end of this thing that we're measuring. All right, well, let's combine these then. Let's take this, fired in for T naught. Let's take that and fired in for T. Okay, so I've got 2 L1 over C times 1 minus V squared over C squared. That's going to equal gamma times 2L naught over C. And I want to solve this for the L1. So the 2's cancel, the C's cancel, right? 2 and 2, C and C. So we end up with L1 equals L naught times gamma times 1 minus V squared over C squared. Ugh. All kinds of issues there. Okay, so I don't know if you remember what gamma was. Gamma, oh, right up here, was 1 over the square root of 1 minus V over C squared. So think about if I multiply that to the 1 minus V squared over C squared, I've got something divided by its square root. So this simplifies to this. And then we can turn that back into gamma. And what this ends up looking like, and I'm going to drop the sub 1. But this is what we end up with the relationships between the lengths. So L naught, that was the length measured by the physicist in the car. And L is the length that we are going to measure outside of the car. So this is what the math says it must be. But I want to talk a little bit about this. So remember what happens with gamma. Gamma gets bigger as we go faster. Right? If we're stationary, gamma is 1. As we speed up, gamma gets bigger. And like we were talking about, like with the 0.99C example, that was a gamma of 7. So think about what this is telling us. L naught, that was the length measured by the person in the car. So let's say, just for the sake of it, we've got somebody in the car lying down on a bed. And that person is 2 meters tall. We outside that train car are going to think that they are shorter than 2 meters. How much shorter? Well, it depends on gamma. We're going to divide by that multiplier, by that gamma number that was determined by their speed. But regardless, we are going to think that they are shorter. Think about this, like what if the train car, what the person in the car measures the train car and says, oh, this car is 10 meters long. Nope, we're going to think it's shorter. How much shorter? Well, divide by the gamma. Okay, so think about what happened with time and now what's going on with length. All right, so we've got the physicist who's in the train car. In terms of proper time, they're keeping proper time. Turns out they're also keeping proper length in this case, and I'll explain that in a second. But what we're going to see, because we're outside this train car, we're going to see these two things. All right, so to us, so this will be our little thought bubble. We're going to say that their time is shorter and their lengths are shorter. Right, because we calculated our time was longer than theirs. And we're also calculating that their length is shorter than ours. So we're seeing both of those things happen. So if a UFO flew by you super fast, let's say a UFO flies by you super fast and you're like, you call up, whoever, and you're like, oh my God, I saw the coolest thing. I saw this UFO. And they're like, how long was it? And you go, I don't know. It was like 5 meters long. In reality, it's longer than 5 meters. You saw it as a length of 5 meters, but it was contracted by whatever their speed was. So was it longer than 5 meters? Yes. How much longer? Depends on how fast it was flying by you.
So in Star Wars, when you see the ship going to light speed from the outside, it looks like it gets smaller. They got that right?
They definitely did get that right. Yep. Now, we do have to understand that they're accelerating. And so like this derivation is assuming constant velocity. However, as it speeds up, we should see it shrink for sure. And lots of movies actually do it right. There are a lot of movies that take relativity into account and do it properly. Not all of them, but many of them do. All right, so whoa, check that out. So not only do times change, but length measurements change as well. All right, so we need to talk a little bit though about like proper length. Who's actually measuring proper length? And how does that all apply here? Because like in this formula, when I wrote this as the L equals L naught times gamma, this L naught, this is proper length. Because again, remember, this is perspective, right? Like while we see the physicist in the train car moving, she's going to say, no, I'm not moving. It's you guys that are moving. And so, we could make the same argument that as she's going by in this train car going super fast, and I've got my dog on my leash and that leash is out 10 feet, she's going to go, oh no, the dog wasn't 10 feet away from you. The dog was actually much closer to you, again, according to the gamma. So what does proper length mean? Well, proper length, this is the length when, or let me say it this way, it's the length in the reference frame where the object is not moving. So if you come back to this example, and we just had, you know, the meter stick on, you know, on board or whatever, the physicist in the train car doesn't see that thing moving, right? I mean, this is a great example. Think about we're on Earth, and Earth is moving, right? We are zipping through the universe right now. However, you're looking at your screen, whether it's a laptop or an iPad or a phone or whatever, and it doesn't look like it's moving to you. So if you were to take your ruler and measure it from edge to edge, that's going to be a proper length. Anyone else who's cruising by you, right? Even some, you know, some kid out there on a you know, on a skateboard that's out in front of your house, they measure your screen while they're moving. That is not proper length, because relative to them, your computer screen is moving, right? If they were to think, well, I'm stationary and the world is going by me, yours would be moving. And so their measurement of your device would not be proper. But if they measured their skateboard, that's a proper length. We try to measure it as they're going by. That's not a proper length. Okay, so proper length is the length in the reference frame where that object is not moving. All right, so that's the first thing. So that's how we know proper length. Just like proper time is start and stop of the event occurs at the same location. Proper length is object isn't moving relative to that reference frame. But they actually completely jive, right? Like think about how we defined it here with that we're sending a pulse to the end and back. According to the person in the train car, right, that physicist sees that event start and stop at the same place. So they calculated proper time and they were measuring proper length in that circumstance. All right, so does that kind of make sense? The idea of, or how we know who's got proper length? I hope.
So do astrologists need to like calculate the objective length because they can't make any sort of like actual measurements of like say a star or the size of a star, so they would have to like calculate the star's real length? I mean, you know, not length, I mean like radius and therefore.
Sure. Okay. So first of all, I'm just gonna have to say, welcome, Jacob. Good to see you here. Not astrologists, astronomers.
Astronomers. I'm sorry.
Astronomer. No, it's all good. Okay. So let's just think about that. So we're gonna say, all right, we see this star out there, and we think that it is, you know, it's got a diameter of much. Okay. That does have, oh, man. Let me try that again. You do have to take into account this for sure, because we observe it and we go, oh, its length must be whatever. That is not necessarily a proper length, right? If that star is moving relative to us. And so we'd have to have an idea of how fast they're moving, how fast that star is moving, so that then we can take that into account, put in our gamma, adjust it, and go, okay, we measured it as it's 100,000 kilometers across, but because of how fast it's traveling, we think that it's actually 140,000 kilometers across or whatever. So yes, I guess the long story short is yes, that is something that does need to be taken into account, which of course leads to that, well, how can we figure out how fast they're moving? But we have a way of doing that, and we'll get to that probably later today.
I'm assuming it's Doppler effect.
It is absolutely the Doppler effect. Yeah. But yeah, no, you're right though, Jacob, in terms of all these things, when we're trying to make measurements, or we want to say, hey, you know, the galaxy is this distance across, we do need to take into account, are we talking about proper distance, the distance we measure? Are they different? Because they may not even be different, right? If relative to whatever that thing we're measuring, we're not changing our position. So, but that is definitely something that we do need to take into account. But that's a good question.
Right. Yeah, sorry for misspeaking.
Oh,
Astrologists
no.
and astronomers.
That's
They're very different.
They are very different, and I'm just standing up for my astronomer brethren. So I knew what you meant, but dude, this is going out on YouTube. I got to make sure that. Okay, so let's do an example, just so you can kind of see how this plays out, and we'll see how we need the calculation. So remember that L equals L naught over gamma, because I'm going to clear all this stuff. But let's say that we are traveling between two stars. So we've got our Millennium Falcon-y type thing. Although we can't actually use the Millennium Falcon. I know that it is Star Wars Day, but Millennium Falcon uses hyperdrive, and I don't know how hyperdrive works. I don't know the physics of it, so we're not going there. But let's say that these two stars, these two stars, someone on Earth, so this is Earth, measures the distance between those two stars and sees that they're 10 light years apart. Okay, so that's the distance between them. All right, now we're going to be in our spaceship. And because this is total sacrilege, I'm doing it. It's Star Wars Day, but I just drew the Starship Enterprise. All right, so we're on our spacecraft, and we are traveling, let's say 0.9 C. So here's my question. According to us on our spaceship, how do these stars appear? All right, so we are going to use the formula L equals L naught over gamma, right? We know that we're going to use that because of our contraction. For 0.9 C, that tells us that gamma is 2.3. Okay, so that's going to be our factor. So I guess really the question is that 10 light years the L or the L naught?
That depends if the stars are moving with respect to each other, right?
Okay, so it depends on, well, we're going to go that they're not moving relative to each other. I don't want to have a variable difference in distance there. So that distance is going to be fixed. So those stars are not moving relative to each other.
I'm thinking 10 light years is L naught.
So say you think 10 light years is what?
Is L naught.
Okay, it's L naught. And it looks like that's what Ralph put in the chat box as well.
Yeah, if they're not moving, then yeah, I'm gonna say L naught as well.
Okay, so think of like, suppose there's a big ass ruler between these stars. Is that ruler moving relative to us in the spaceship?
If the spaceship's moving, then yes.
Okay, and the spaceship's definitely moving, right? We're cruising from star to star.
I'll be right there, Captain.
Okay, so the 10 light years is moving relative to the spaceship. So that's not an L naught. To us on Earth, because we're not moving relative to the stars, or so little that we can't even notice it, that 10 light years is L naught. So on this spaceship, what we're going to see is a distance of 10 light years divided by 2.3, which is around 4.35 light years. So think about that. We're on that spaceship cruising by, and that star out ahead of us, we're going to go, oh, that's only 4.35 light years away. When someone on Earth is going to go, what the hell are you talking about? It's actually 10 light years away. So this is something else they never talk about in sci-fi movies. And I mean, I understand why they don't, but I think it would be kind of interesting is, you know, because they always have like the star charts. So when they're navigating, they're like, oh yeah, okay, this, that star, blah, blah, blah. You know, how far away are we? Oh, well, we're so distance. They never take into account that if you're on that spacecraft, whatever star charts you have from Earth, useless. They're useless because you're not going to see it that way. You're not going to see this star 10 light years in your, you know, ahead of you. You're only going to see it 4.35 light years ahead of you. All right, so then you might start going, all right, well, this feels like it's a problem because according to them, it's only 5.3 light years, and the light going from one star to the other, then it's only going to take 4.35 years, but to someone on Earth, it's going to take 10 years. And that might feel like there's a bit of an issue there, but remember time dilation. You send that pulse, a light pulse from one star to the other, on the moving spaceship, it's going to time it at 4.35 years. On Earth, we're going to time it at 10 years. But yeah, time doesn't progress the same. Time's going to go longer on Earth than it is on the spaceship. So even though it starts feeling like things don't match up, it all ends up working out mathematically when you allow for that adjustment in time. And I would say that that's one of the things that caused me the most trouble when I first learned about relativity. Because I would go to just classical mechanics and be like, all right, distance, time, dirt kind of formulas, and things didn't match up. And I forgot that the T's are not the same T's. So if you do a dirt formula for someone in the spaceship, and you do the dirt formula for someone on Earth, accounting for the change in time due to time dilation, everything works. Because everything is built off of it, right? I mean, if you look at what we've done mathematically, I mean, this is it. We drew the right triangles and, you know, did whatever calculation. And then from there, it's just been like simple dirt and substitution and all that. We just have to keep reminding ourselves times are not the same. Times are not the same. And if times are not the same, then lengths are not the same. And then we're going to see real quick that velocities are not the same, and so on and so forth. Okay, so there's your third big consequence, right? If you've been keeping track. The first was simultaneous events are not necessarily simultaneous. Second one was that time doesn't progress the same way. And the third one now is that lengths aren't measured the same way. All right, so, you know, when I hold up this pen, my length and your length may not be exactly the same. But you can see why it's not a problem if we're going at slow speeds, because remember gamma, if we're stationary, gamma is 1. And then it's like, okay, yeah, if the spaceship is just sitting there, starship's just sitting there, not moving. Of course, they're going to see it as 10 light years apart because so did we. Right? But even at slow speeds, you may remember that the gamma, it takes a while before it gets like noticeably different. I mean, even at 1/10 of the speed of light, it's close enough to 1. That's why we don't see this. That's why it doesn't affect us in everyday life. But if we're going to travel at high speeds, we got to allow it. All right. So now what about velocities? How is this going to play out when it comes to velocity? So let me do this. I'm going to clear this. And we're going to start with what we call the Lorentz transformations. And what these are going to be the way that we translate the coordinates, the space and time coordinates, in one frame compared to another. Okay, so here's basically what's going to happen. We're going to have one reference frame that's stationary. Okay, so this is going to be X. Let's go with Y and Z. And I'm going to call this frame S. And this is the one that's stationary. Now, in here, we're also going to have another frame that I'm going to call S prime. So in terms of its axes, I'm just going to call them X prime, Y prime, Z prime. And the thing about this reference frame is that it's moving. And it's going to be moving with a velocity of V. So if we were to take just some point out here in space, right? This is going to have coordinates X, comma, Y, comma, Z, comma, T. So we're going to now look at space-time coordinates. So the first three are just the coordinates according to the red coordinate axes, and then T is going to be the time according to that coordinate axis. But it also can be represented as X prime, Y prime, Z prime, T prime. And that second set, these are the space-time coordinates according to S prime. So kind of the way to think about this is if, so we're here on Earth, and let's say Jesus is in a spaceship going flying somewhere, and a star goes nova, and we're communicating with them. We would say we saw that nova occur at coordinates X, Y, Z at a time of T. And for him, he's going to say, well, I saw it at X prime, Y prime, Z prime at the time T prime. Okay, so that's just how this is going to play out. So all the ones with primes are the coordinates and the time relative to the person who's in the moving system. Okay, now if you think about Galileo and how we do transformations if we're not dealing with relativity, this is actually like really easy, right? For the Galilean transformations, Y and Z and T are all going to be the same. right? If we just go with Galilean, regular old, easy physics stuff, and Jesus tells us where he saw that nova and we tell him where we saw it, our y's and z's are going to be equal and our t's are going to be equal. The only difference is going to be our x's, and the x location is really going to matter, like v, how fast he's going, right? So it's really easy if this was just regular old Galilean. The only thing that we'd have to change is our x, and then it's only going to be off by a v times t, right? How far did that actually move? Well, it depends how much time has occurred and how fast it's moving. Okay, but let's think about this now relativistically. Now, times aren't the same. Lengths aren't the same, which means, oh, good Lord. Oh, good Lord. Go ahead and build these. We're going to build the conversions between them, but I need to tell you something, some good news. Wait, we can use some good news right now. All right. The y is going to equal y prime, and z is going to equal z prime. Because all of that length contraction that we were talking about, that only has to deal with lengths that are in the direction of travel. All right, so that's such an important fact. I should probably put that up here. All right, any kind of length that's perpendicular to the path of travel is unaffected. Can you see why? Like, why is it that I don't care about the other lengths?
Well, we're not moving in that direction, I guess.
Yeah, that's exactly it. Like, you think about how we had it set up, right? And we're going to send a light beam from one edge to the other and back. If I'm doing it this way and the pen's moving, I'm not going to see the same effect. I'm not going to see that top mirror moving away and increasing the length, right? I will see a change in time, but again, that's due to the time dilation effect. But I'm not going to actually see a change in the length. And the same thing if it was coming in and out towards you, right? As it's moving this direction, there won't be a change. All right, so that's some really good news. So if, again, Jesus is out there on that spaceship and we're on Earth and we're communicating, we don't have to worry about those two coordinates being affected. We only have to worry about the coordinate in the direction that he's traveling. Okay, so let's see if we can kind of figure out the relationship between them. So let's start looking at X. All right, so on our picture, this right there, that is the X coordinate. Right, that's the coordinate relative to the red frame. Now, what I want to do is I want to split it. I want to build it. And I'm going to build it by breaking it into pieces. So let's look at, there's this piece. And there's that piece. So X is going to be the sum of those two. Now, this first piece, that's going to be V times T. So if I know how fast that coordinate system is moving, I multiply it by how long it's gone, and that tells me how far it went. All right, that's just good old dirt formula. Distance equals rate times time. And then what I need to add on to it is the x prime, right? Because you think about this piece, that's going to be the x coordinate in the moving coordinate system. But before you get too excited and be like, okay, that's all we got to do. Okay, that x prime, that's the distance in the s coordinate system, right? In the s prime frame. But the s prime frame is moving. So I have to change this length so that it's the length that I would observe if I was the stationary person. So x prime, that's a proper length, which means for me to get the length, I have to divide by gamma. And that's where this relativity stuff gets weird. Right? Up to that point, I think you guys were all on board. You're like, yeah, sweet. Okay, so it's that extra distance from the dirt formula plus the distance in the coordinate system. But what Jesus is measuring in his system is not the same as what we would measure. We have to adjust by dividing by gamma.
Is this a differential equation?
No, it is not a differential equation. These are not derivatives. These are just, I'm calling it x prime because it's a different world. But none of these are derivatives. None of these things are changing. I'm assuming that the velocity is the same, right? That it's that he's not speeding up in his spaceship because I need it to be inertial. And the gamma is determined by how fast he's going. And then the t and the x prime, those are just things that we calculate. We're not calculating changes in them. So, so it is not a differential equation. I know it looks like it because of that x prime.
Yeah, it's just my brain's programmed to see that prime and then
And
off on a tangent with that.
Trust me, I get that. I totally get that. All right, so, but check this out. This now will allow us to see the relationship, right? I mean, x is actually equal to this. Now, what I want to do is I want to create a set of conversions where we can figure out what the one set is relative to the other. So I'm going to do here, let's do x prime equals, y prime equals, z prime equals, and t prime equals. We already know that the y and the z coordinates are the same. But we can now solve this for x prime, and we get it as gamma times x minus vt. If you just move that around. So basically, this would be how we would, like when we communicate to Jesus on the spaceship, and we say, all right, hey, Jesus, we just saw 5 seconds ago, there was a supernova that was at these coordinates. If he wants to know when to look and where to look, he's going to use these formulas. So he would plug in, okay, they gave us, they just sent me this x coordinate, and they said it was at this time. All right, I know how fast I'm going. I know what our gamma is, calculate. So I should look in my reference frame at this distance. So like if we said, yeah, we see it 10 light years ahead of us, he would run the numbers and go, okay, it's not actually going to be 10 years ahead of me. I'm going to see it at this number according to this formula. Okay, so he's got the x on the y and the z, but now he's got to get the t. And the t, well, this one is just going to come from the conversion that we saw before, right? And the way that you're going to get there is this, is think about it from the other perspective. let's think about it from Jesus's perspective. So he's going to go, okay, well, let's just look at this distance as x prime. That x prime, that's going to equal the x minus how far I've gone. But he's going to do the same thing where he has to take that x and divide it by gamma, because that x is how we on Earth are measuring it. So that's a proper length according to us. He's got to divide by gamma. But then he's going to subtract off the speed times his time that's passed. Right? Because he's going to go, oh, I've been going, 0.9 C for the last. All right, so I'm assuming you guys can hear me here. My phone
Yeah.
just took, my computer just went, "Bah." So let me hop up here. By the way, yes, start Father, Son, Holy Spirit. And, so I don't know where.
Oh no, he's frozen again.
Am I frozen again?
You were for a second, now you're back.
All right. Soon we're not going to be in the Zoom world anymore. We don't have to worry about it. Okay, anyway. So what was the last thing that I was saying? Did I give you that? Did you see the perspective from Jesus's view?
I think so. I mean, we hear that he needs to use those formulas to know where to look.
Okay. All right. So let me just sort of recap where we were. Right. We had x prime equals gamma times x minus vt. Y prime was y. Z prime was z. And we were going to get a t prime, right? We're going to see what the time is according to Jesus. And so the way we're going to do that is we're going to actually look at this from both perspectives, right? According to us, we had the x prime was going to equal this. But if you look from Jesus's perspective, here's how this is going to look. He's going to go, all right, on that picture, x prime, his coordinate was going to be made up of two things. It was going to be made up of the x that we on Earth measure, but we have to take away the distance that he's moved. All right, so we're going to have x minus and the distance he moved is going to be v times t prime. Right, so he's got his stopwatch and he's thinking, okay, I've been flying at, this speed for 2 months. I multiply that speed by the 2 months. That's how far my coordinate system has moved. But remember that x is the distance as measured according to us on Earth, which is a proper length. So he's going to have to do the same thing where he divides by gamma. So this is very similar to what led to this guy. We're just looking at it from the different perspective. All right, well, if you take these two, you can set them equal to each other because they both have x primes. So you get the gamma times x minus vt equals x over gamma minus v times t prime. And then what we're going to do is we're going to solve this for t prime. Right? We can do that. If you do that, and I'm not going to bore you with the details because you know how to do algebra. But what you get for the t here, for t prime, is that that's equal to gamma times t minus v times x over c squared. That's just how it plays. So again, we give Jesus the coordinates and time when we saw this thing happen. He's going to have to use these formulas to adjust to let him know where and when it happened according to him. And that's also a really trippy thing to think of, that it's now no longer just where it is might be different, but when it was is going to change. And it changes according to this formula. All right, so these are the formulas he would use to take our numbers and convert them. And we could actually build a similar thing to go the other direction. I'm not going to bother deriving it, but it's basically built exactly the same way. But there are conversions to go the other direction. So if Jesus sent us a message and said, hey, here is something I saw with my coordinates, we could convert it back. We take his numbers, put them in for x prime, y prime, z prime, and t prime. We do our calculations here, and that'll tell us where and when. But if you look at them, they should all make sense, right? Instead of the minuses, they're now pluses as we're going the other direction. But yeah. So these are called the Lorentz Transformations. And they are what we have to use when we're dealing with relativity. All right, so I know what I told you we were going to do. We're going to look at velocity. We still haven't looked at velocity yet, but now we're ready to. Now that we see the relationships between x, y, and z and t, now we can go ahead and calculate what's going on with velocity. So let's do that. Let's actually look at how velocities are related. So I want to go ahead and leave these up here because we're going to use those to calculate our velocity. I'm going to erase the other ones. But let's think about velocity and how we calculate. Okay, so I'm going to go with it as u prime. So this is going to be the velocity as measured by Jesus as he's going. I'm using u instead of v because we're already using v for the speed of the reference frame. Okay, so this is going to be a dx prime dt prime. It's the change in position compared to the change in time in his reference frame. All right, well, let's convert those using these formulas into our stationary reference frame. So we're going to get gamma times dx minus v times dt divided by gamma times dt minus v times dx over c squared. So that's the incremental, the little differential chunks of x prime and t prime, but written in terms of hours. All right, so let's simplify this. The gammas are going to go. So bam, bam. And then I'm going to divide everything by dt. So that's going to turn this into dx dt minus v over 1 minus v over c squared times dx dt. Now, dx dt is going to be a velocity that we measure in our stationary reference frame. So I'm going to change that to u. So we get u prime equals u minus v over 1 minus u times v over c squared. So that's the velocity relationship between velocity measured in a stationary reference frame, that's the u, and the velocity measured in the moving reference frame. So basically, this is how this would play out. Let's say we saw a comet. And we go, hey, Jesus, be on the lookout. There's a comet that's moving towards you with this speed, whatever speed we say. He would take the speed that we told him, put that in for you, using the speed that he's moving at v, do that calculation, and that would be the speed that that comet is going to move relative to him. Okay, so that's how that formula works out. Now, it turns out you can do the exact same thing if you use the other calculations and do a dx dt and turn it into x primes and all that. I'm going to save that effort for you on your own if you want to see it. But if we go the other way, u is going to equal u prime plus v over 1 plus u prime times v over c squared. And so this would go the other way. This would be if Jesus saw something as he's cruising out there and said, ooh, this is moving at this speed, we would plug that in there and we'd know what speed it's moving relative to us. All right, so again, the math isn't complicated here. It really isn't, especially compared to a lot of what else you've seen in physics. But the ramifications of this math are pretty mind-blowing. So let's do a couple of examples using these transformations, just so that you can kind of see how we get some weird weird results, and where, some funky stuff happens. All right, so here's the first one we're going to do. Let's say that we're in some sort of a race out in space, right? And so we're in the Millennium Falcon, and we're cruising nice and fast, and we reach the finish line. And as soon as we reach the finish line, we got somebody who's in the back of the Falcon, that sends a message that goes, hooray, we won. And so for us in the Millennium Falcon, let's say that this is the finish line. And we're going to see how this goes. Except for the Falcon. Oh, that's bad. That's the Millennium Falcon. Go with it. That's Millennium Falcon. But here's what we know about the Millennium Falcon, right? We measure this, and I have no idea if these numbers are correct for the Millennium Falcon, but we're going to go with it. I think it's way too big. But, well, no, just how about we'll say that this distance is 30 meters. And I'm going to say, according to us in the Falcon. All right, so we would say that our spaceship is 30 meters long. Okay, so we're 30 meters long according to us in the Falcon. And again, there's going to be a signal that's sent from someone who's in the rear that says, we won. Except it's not a thought bubble. It's we're saying it. We won. All right, now, the other thing I want you to know is that the Millennium Falcon, we are moving at 0.6 C. All right, so here's what I want to do. I want to know, to someone who's watching this, right? So maybe one of the Huts is watching, because you know how they like to gamble. So one of the Huts is watching. I want to know, according to someone out here, where and when was the we won signal sent?
Did you say where or when it was sent?
Yes. Where and when.
Got it. Okay.
So I want to know both. All right, so let's just start labeling some things, because I think that will help us. In terms of the moving reference frame, the moving reference frame is the Falcon. So all the numbers according to the Falcon are going to be primes. All right, so in terms of where that signal was sent, that signal was sent at -30 meters. I'm going to go with the finish line as 0. So when that signal was sent, they were actually 30 meters behind the finish line. So that's why X prime is going to be -30. I don't care about Y and Z because they don't get affected here. So I'm only going to look at X prime. And then T prime, when that happened, I'm going to say is 0 seconds. All right, so according to us on the Falcon, that happened instantaneously. It was right as we were crossing. So I'm going to say that that happened at time 0 seconds. All right. So we've got that. And then the one other thing that we know is that our V is 0.6 C. Okay. So, and this is the V that we were talking about, is the speed of the reference frame. So 0.6. All right. So in order to answer this question, we need to calculate what does x equal. That's going to be the position according to the stationary reference frame. And then what does t equal? That's when did this happen? All right, so let's do the calculation. So if we go to the x, for the x, we need a gamma. If v is 0.6 c, that makes gamma 1.25, or roughly 1.25. Okay, so that's the factor that we're going to use for 0.6. All right, so here we go. So x, it's going to equal gamma, so 1.25, times x prime, so minus 30 meters, plus c or v times t. We're going to plus 0.6 c times t prime, which is going to be 0. So I'm just punching those into the form. All right, well, the times 0, of course, makes that 0. Multiply the 1.25 times 30. And what we get is minus 37.5 meters. So we're actually going to believe that it happened, like as we're watching it, that this signal was sent a little bit further back.
Seems kind of reasonable.
Because, I mean, think about it, as that signal is sent, they're still moving forward and, okay, yeah, whatever. So we already know that lengths get weird anyway. So. All right, so that's what x is going to equal. So now if we calculate t, we do exactly the same thing. We go to that formula. So t, that's going to equal gamma times all right, so we go and we look at that one. We're going to get, oh, why did I write gamma? I meant to write 1.25. We're going to multiply it by t prime. So t prime is 0. And then we need to add to that v times x prime over c squared. Okay, so the v was 0.6 c times x prime minus 30 meters. And then again, divided by c squared. All right, so run the numbers on that, and you should get something that's around negative 7.5 times 10 to the minus 7 seconds. So what is that? That's like negative 75 microseconds. Okay, now this is the one that feels weird. It feels wrong.
Negative time.
Yeah. So think about what this means. We're going to say that that signal was actually sent before the person in the Millennium Falcon sent it. What? And this feels wrong. This feels totally wrong.
He used the force.
Yeah, right. It was. So we use the force to travel through time to send our message. Okay, so obviously we don't want to have to use force. We want to be able to just use physics. All right. This is okay. This is totally okay because I want you to think about a couple of things. First of all, what was the first thing I said that was a consequence of relativity?
Time was it wrong or off? It was different.
It wasn't time. What were we talking about before time even?
It was trippy.
I'll go for it, Jacob.
Actions that we would think of as happening simultaneously wouldn't happen simultaneously.
Okay, so simultaneous doesn't mean simultaneous anymore. Think about the perspective of the people in the Millennium Falcon. Whoever's riding in the back that goes, hey, we won. They sent that signal as they were crossing the finish line, simultaneous, right? We outside of this world are not going to think that those were simultaneous events. Because of the fact that they're moving at 0.6c, we are not going to think that that signal was sent as at exactly the same time as they crossed the finish line. So the fact that we're getting a different number here, first of all, should not throw you. We should expect that, but they're not simultaneous. Now, the fact it's negative, we need to still kind of justify that. However, that one also is not that big of a deal if we kind of think about it. Right? So, first of all, we're watching this happen. How long do we think this spaceship is? What length are we going to see it as? Are we going to see it at 30 meters?
No, it'll be smaller.
Okay, it's going to be shorter. So we already think that it's less than 30 meters long. Where did we think the back of it was? Well, we thought the back of it was still 37.5 meters behind the finish line. So when that signal was sent, what we are going to see as these observers outside of it, if this is our finish line, we are going to see the back of this Millennium Falcon be a little bit further back. And we're also going to see it shorter. It's no longer 30 meters long, it's shrunk. So yeah, we should totally expect that that signal happened before it crossed the finish line, according to us. Because it's already shorter and it wasn't even there yet. All right, now I know that this doesn't really help because we're still all like, oh my God. But it all matches. It all works out when we think about all of the consequences of relativity. But just on its own, it feels wrong, right? Oh, they sent that signal before they even finished. Well, yeah, according to us, they did. They weren't there yet. They hadn't reached the finish line. All right, well, if we ever get to the point where we start having races in space like this is something we're going to have to take into account. Because here's Han Solo and the Millennium Falcon being like, the race is over, I've won. But us out here are like, you haven't even finished yet, man. You're still not there.
Maybe you could, like, I don't know, use quantum entanglement to like flip a particle to let him know.
Yeah, well, I mean, here's the other thing though, is like if Han Solo's seeing that he won compared to all the other people that are going around his speed, we are definitely going to see those other people back behind, and I don't think it would actually end up mattering. But it's one of those things. So this was an example that just had some positions, time, space positions. Let me show you what happens with velocity, because this is kind of trippy too. All right. So for this example, we are going to be in a spaceship that sends out a probe. Okay. So here's Earth. We are in our spaceship that's cruising out here. So again, just because I like drawing them. I'll do the Enterprise again. All right, so we're out here. And we are moving 0.9 C relative to Earth. Okay, so we're cruising at 0.9 C. So we see some sort of weird anomaly out ahead of us, and we send out a probe. Okay, our little probe. And this probe is going to be moving at 0.7 C relative to the spacecraft. So we're sitting on the bridge of this spacecraft. When we see our probe go out, we're going to go, oh, that thing's moving at 0.7 C. So here's the question. What is the speed of the Earth, or sorry, speed of the probe relative to the Earth? Now, this is one where we can't use classical mechanics, right? Because what would the answer be if we just did Galilean classical stuff?
The distance and the time.
Don't worry about distance and time so much, but just like speeds, right? Remember the whole, if I throw the baseball out front of the moving car, what do you normally do with those speeds?
You just add them.
Yeah, you just add them. And as Ralph just said in the chat, the probe is going to be going faster than light, right? We would add those together. 0.9 plus 0.7 is 1.6. And so classically, this would be saying that that probe is moving at 1.6 times the speed of light, which can't happen. But I want you to see that relativity, that the transformations and everything make it so that we're still okay. Everything's going to work. So let's go back to that formula for U, right? Because we want it relative to Earth. So in our formulas, that's the U formula. So we're going to use U equals, and we had U prime plus V. I might have had it written the other way. I'm not really sure. But we had U prime plus V over 1 plus U prime times V over C squared. So let's put in all those numbers. So the U prime, that was the speed relative to the spacecraft. So that's going to be 0.7 C. And then V was how fast the spacecraft was moving relative to Earth. So the speed of the frame, which is 0.9. And then on the bottom, we're going to get 1 plus 0.7 C times 0.9 C, all divided by C squared. So down here, all those C's cancel. So we're left with 1.6 C divided by 1.63. So you take the 0.9 times 0.7, And this ends up being 0.98 c, which is still under our cap, right? We can't go faster than c. So it turns out that it works. These transformations ensure that you'll never go faster than the speed of light. All right, so that's how fast we would say it's going, is actually 0.98. Fun fact, let me just show you this real quick. What if instead of sending out a probe, we sent out a light beam? We start shining a laser. So instead of 0.7 C, let's just make that C. I want you to see what happens if we do that. How about before we go to the formula, what should you expect?
1C.
We should expect an answer of C, right? I mean, this is the fundamental bit of relativity, is that C is C is C is C, no matter what world we're in. Well, check out what happens with this formula. So if we do this, we're going to get U equals, okay, well, now it's going to be C plus 0.9C over 1 plus C times 0.9C over C squared. Well, that's 1.9C on top. On the bottom, the C's all cancel. We get 1.9. And that equals C. And that will always happen. So that's kind of nice, actually, that these formulas work out that way, because they have to, or else they're no good. So that's just a little more justification for why these formulas work. But they have to. Like, I mean, the math says they do. And it was all based on that simple little triangle. We got our light bouncing off the roof and coming back down. So a very small amount of math brings us to some very real results. All right, so I think we're going to stop here. We're just about out of time, so I think it's a good place to break. So we're going to keep talking relativity. We're not done yet, because I do want to talk about the Doppler effect, how we can tell how fast things are moving, so that then we can use that to adjust, like when the question came up earlier about what was it you asked Jacob something about stars? I forget.
Yeah, it was how do we not like find out the actual size of a star?
Right, the actual lengths compared to what we measure. Right. So we have to know how fast they're going so we can make those calculations. Well, the Doppler effect, which we already know is a real thing with the wave, so it should still be a real thing. Well, we'll see how relativity affects that. And then we'll also talk about momentum and energy, and then be able to move on. Okay, so expect on Thursday, we're going to do one more day talking about relativity. In terms of quizzes, I think we're going to go a week off of quizzes. We've been doing pretty well with them. I haven't even graded that other one yet, so I'm not going to give you another one. So no quiz on Thursday. We'll just plan on being in here at the usual time at 4 o'clock. All right, and we'll talk relativity and then who knows what. All right, but no quiz this week. But we're still going to have an exam next time or next week. Right, we're still going to be on tap for that. And just so you know, plan on that being chapters 1 through 5. So all of the optics and then relativity. But we should be done with relativity on Thursday, which will give you plenty of time to do problems and kind of get that down for that exam. Okay. So I think that's all I've got to share with you guys in terms of where we are and what's going on. No homework due tonight. Chapter 4 is actually due on Thursday. All right. So with that, have an awesome couple days, and I'll see everybody on Thursday. And again, happy Star Wars Day.